How's everyone doing? The last day of ISC here. This presentation is going to go over the AI pipeline and how to architecture high-performance storage, because right now it needs a redesign with how everything's moving. What does VDURA stand for? It stands for Velocity Meets Durability. There's a couple different things AI workloads and HPC workloads need today. They need high performance, which is velocity. They need durability, which we're the world's strongest data platform. And the last thing is resilient value tier capacities. My previous experience, I spent 3 years at a early stage AI artificial intelligence company. And we were using GPT-1 in the product. So this was a few years ago, right before ChatGPT took off. So I got to see every evolution of these generative AI models and build on top of it. So I bring an interesting view. Now at VDURA, we're on the infrastructure side, making sure those models move efficiently for data storage. Research labs are implementing AI, GPU clusters at record paces. They're trying to figure out what does the future look like, and they're preparing. There's exponential growth in the model sizes and the compute intensity. So you're planning, how do I satisfy the power requirements? What are costs gonna look like? How does my storage look with the GPUs that we're implementing right now? So what is the growth like? It's wild. Some of you out there may know, but now it's getting to 18 trillion data points in some of these new models. What's the growth rate? 2.5 times year over year. So what does that look like in a couple of years? Crazy. The second thing is the power consumption of these new data centers that are being built are going to be the size, and I should have used a European city here, but they're going to be the size of San Francisco in the near future. So imagine one data center using the same amount of power as San Francisco. How do we prepare for that? So what's going on with the current trends? One is there's breakthroughs in the models. The fun part about if you're using the generative AI models, you'll notice one of them makes a breakthrough and then the rest of them make that breakthrough like 2 weeks later. It's like rapid pace, they're learning from each other. And then we have the rise of foundation models, demanding massive storage and rapid retrieval, and a lot of people are using these foundation models in the enterprise. There's an increasing emphasis on real-time inference. That's where you're seeing a lot of storage. Future storage preparation for right now is preparing for inferencing workloads. People are looking at the environmental impact. How do I sustain my cost? How do I protect the environment? How do I not use too much power? So what is the AI pipeline? And I'm gonna talk about this from a data storage infrastructure standpoint. First, you have the data collection stage. You may have a huge data lake with all your data in it, or you're collecting data directly from the client devices, IoT devices, etc. So you're storing that data, then you're pre-processing, making sure it's usable, and you load your model. You're going to need, each one of these stages requires different storage infrastructure requirements. Some of them need very fast speed. Some of them you have to hold data for long-term retention. They have different demands. We'll show later on reads and writes. When you're preparing for your data storage infrastructure, a lot of people are just looking at read speeds. Well, writes are equally important, so make sure you look at that. After model training, you're doing checkpointing. Checkpointing can occur as much as every minute to frequently. So during the checkpointing, one of the major things that you keep hearing over and over again is GPUs remain idle. So when you're spending millions and millions on GPUs, every second your GPUs are idle, you're burning capital. And then the pipeline keeps going through fine tuning, which has checkpointing, which is smaller, and then finally inference and production deployment. And some of these stages could be happening simultaneously. So you have to prepare for all these different stages. This graph right here shows you a little bit about how the workloads look differently across the AI pipeline. You'll see data ingest, very write heavy. Your model load, very read heavy. Training, mostly read heavy. And then your checkpoints are these fast bursts of write. And what do you need there? You need extremely fast speeds because your GPUs are sitting idle and you're wasting money. You train again, this is an abbreviated version, but the checkpoints occur frequently, then fine-tuning has smaller checkpoints, and then inferencing is very read-heavy. As you prepare your infrastructure, you need to be looking at all these different stages. How can I satisfy the requirements? Sometimes it may be good to get good enough performance to the place that you have no bottlenecks, and then prepare for capacity. This goes in a little bit more details about the different data sizes for each of the stages and what the stage is and how heavy the workload is. So what's going on? Why do some architectures fall short? So first, you'll hear a common struggle out there that centralized storage bottlenecks have a head node. So some of the not truly parallel file systems out there have this head node bottleneck. Think of it as you trying to take a shower, you're really tired out on this trip, and you're trying to take a shower, and all you have is this little faucet. It's hitting you from the top of your head. That's not a very good shower, right? So with a parallel file system, it's like a shower head or multiple shower heads distributing the data directly down to all the storage nodes very efficiently. So you can utilize the performance of all of it. The second thing is you can have metadata overload, so the data about data, you have to prepare how does it know where everything is to get to the right place or retrieve it. The third is GPU waste during these checkpoints. We talked about that. A fourth is utilizing, so one of the major challenges you hear with AI, now I know most of the audience here is HPC, but one thing that companies are doing is they're just preparing for that performance criteria. We'll look at it, there's really three criteria. The main thing people are thinking it through is GPU optimization. Can my storage meet the needs of the GPU? The second is capacity and how does my data infrastructure look in the future? Well, people are just focusing on performance, going all flash, and then there's waste because you don't need it for every stage. Finally, manual tiering capability. So how does the data tier? Can it land on flash and then manually tier down to a more cost-effective bulk storage? With this, there can be lots of challenges. You have to prepare for this. So you got to start rethinking how does data infrastructure look in the future. One is you have to prepare for scalability. How easy is it for me to add a node, for example, or expand the performance or capacity or the management? Intelligent data tiering. Can I autonomously tier this data? Third, again, scalable. Is it linear and predictable? If I need this much more performance, can I do it easily? Finally, resiliency and security. I actually read another study that's like 70% of AI workloads are impacted by some sort of data outage. Whenever you lose data during a checkpoint, you have to start from the very beginning, so it can be very costly. That's one reason why you hear about Vidura, velocity meets durability. We care about that resiliency. You lose one object in a trillion with some of our scaled out systems. Smart orchestration across the pipeline. So the future and right now, you have to really look at AI-aware data orchestration to continuously adjust the pipeline to needs. Real-time tiering. You want the most active hot data to land on flash, and you want to autonomously tier the data to cost-efficient bulk storage without having to think about it. You want infrastructure responsive to checkpointing bursts, inference peaks, and GPU utilization. So on the right, you're going to see a couple of, in this data rack, you're going to see a couple of different nodes here. At Vidura, we have a separate control plane and a data plane. Our director nodes run a software called Velo, which is a metadata engine, a key value store, separate from the data storage. The bottom two sections there is, the top is our all flash storage with super high performance for those high performance needed AI stages. You'll see right to the left there, I've actually outlined the different colors of which storage capacity or technology aligns with those area of the pipeline. And then finally, we have the all flash with our capacity extension. It's a great bulk data store, but it has this flash front end, but it's much more cost efficient. When we look at this, we're driving innovation through this. You can see on the top one here with performance, you can seamlessly add our flash nodes for performance. You'll see the more flash nodes you add, we have a great cost per performance. And then the bottom one here is our capacity. You can go all flash, your cost per terabyte is a little bit higher. You're gonna have extreme performance, but you can really play along that whole line with mixed configurations of capacity expansion to get to that performance level where you do not have bottlenecks, but you're really optimizing your cost per terabyte. So we play best price performance, seamless scalability, and ability to either add performance, capacity, or control seamlessly. So the three really big things, looking at a new blueprint for your AI pipeline needs. First, prepare for the growth in AI data and energy consumption. Second is, how do I optimize for that AI pipeline? You saw each one of the stages, they have different requirements, many of which have different read and write requirements. So when you're planning your architecture, make sure you look at what are the write performance for this, because some of those stages are extremely write heavy. How do I lower those performance trade-offs we discuss? Thank you.